Well, I think it's official. Welcome back, folks. We can begin at this moment. We're currently in section 4.2, and chapter 4 has been titled Applications of the Derivative. So far, the only applications we've been looking at are mathematical ones. So we looked at maximum minimum values. Here we're going to look at more information dealing with graphs. And then in section 4.3, even more information. We'll look at increasing, decreasing test. We'll have a test to find local minimums and maximums. We'll also look at issues with concavity and how to test for concavity as well. So far, the first 3 sections, all about graphs and their functions and how the derivative affects those graphs. But when we come back next week, we're going to be looking into issues with limits once again. It turns out some limits that we didn't do were very hard because you need extra tools, and the derivative can help us and take an actual limit itself, an ordinary limit. So that's what we're dealing with so far, but so we'll also have real world applications as well. They won't all be like these ones so far. Any questions, folks, before we jump back in? Okay, so in these notes, we're doing 2 big theorems. One is called Rolle's theorem. The bigger one is the mean value theorem. They're related, and the mean value theorem is a better version of Rolle's theorem in a certain sense that it applies to a wider class of functions. So to start this off, let's take a look at how Rolle's theorem goes. Well, here it is. This is the entire theorem in its full glory. It says, let f be a function that satisfies 3 hypotheses. F has to be continuous on a closed interval. Now, what this means is it's continuous on all numbers between a and b. But once you go to the left-end boundary point at a, it's continuous only from the right. You can't come in from the left. At the right boundary point B, we're continuous only from the left. So being continuous on a closed interval does have that weird provision for the boundary points, but ordinary continuity for everything in between. Second condition is f has to be a differentiable function. On the open interval, we never define differentiability on an endpoint like we did continuity. And the third thing is the function has to match at its boundary points. F of a must be equal to f of b. Let's think about those conditions once again. F of a equaling f of b is not so bad. We just go to the supplied interval and check that the function matches on both of those numbers. So if it's 0 and 1 up here, you have to show that f of 0 equals f of 1. Here for continuity, we just have to be able to draw that curve without any holes, any jumps, any infinite discontinuities or things like that. So let's just say here, the curve must have no holes, jumps, infinite discontinuities. Well, actually, let's just call that vertical asymptotes. That's what we mean by infinite discontinuity. I'll call it here vertical asymptotes. So just a nice curve that you could draw without ever lifting up your pencil or pen. For differentiability, we're also excluding stuff. And if you're differentiable on AB, you're automatically continuous on the open set from A to B. But here it had also the extra condition, continuous from the right at A, from the left at B. But for differentiable, that means there can't be any cusps, there cannot be any holes, no sharp corners. It has to be fully continuous. So differentiability here means continuous. And to exclude all the corners and cusps, I'll just say smooth. It has to be a nice smooth curve, continuous and smooth. So if we satisfy all these 3, these are the 3 hypotheses in Rolle's theorem, then here's the conclusion. There has to exist a number c in the open interval AB. This excludes the boundary points. We should say that right here. C is not A, C is not equal to B, but you'll be able to find such a number C such that the derivative at C must be equal to 0. In other words, Rolle's theorem is giving us a critical number, and it tells us there has to exist a critical number. It even tells us more. It tells us that critical number, it doesn't only exist, it must be inside that interval from A to B. But that's what this is. We can say here, there exists a critical number, and that critical number is bigger than A and less than B. So that's finally the content of Rolle's theorem. At least reading through it and just looking at it analytically, what all that information is saying, the next best thing to do once you see a technical theorem like this is draw a picture. The textbook always does it for us, which is nice, but honestly, in a certain sense, they're taking away that skill from us. Sometimes it's good to just practice these even after you've read the theorem before, seen the illustration the author drew, because if you can illustrate it yourself, then that is a really good bar to say you have really good understanding of what it's trying to say. So we have the description. Let's see if we can illustrate it. We'll start with the hypotheses and what they have to do. My illustrations on all of these theorems are really going to look like this, just thrown in quadrant 1 so we don't focus too much about the axes. It's less about the axes. I want to start right here. The function has to match at the boundary points. F of A has to be equal to F of B. So I'll draw this function. Let's go with maybe green. We can put our height, F of A, here. We're just putting it in a random location. This is just one example of a function that would satisfy Rolle's theorem. So there's F of A, its value on the y-axis. It has to match the height of F of B. So now I have no choice on this point. It must go exactly at the height F of A was at. We could just write over here, F of A equals F of B. So that's condition 3 already from Rolle's theorem. Now, when I draw the curve, I just have to draw it in a sensible way. I can't do anything crazy. There's no discontinuities. There's no sharp corners. I'll just draw, just a generic curve, kind of go like that. Looks like a semicircle almost. You might have drawn something different. It just has to connect point to point in an ordinary way. So that's the hypotheses. And this, where it starts in blue, is the conclusion. It says there must be a number C in the interval from A to B, excluding the boundary points, but the derivative of f at C comes out as 0. Well, we have such a number. On this plot right here, we have to indicate where it actually would be located at, but some people might already see where it should be just by considering the graph here and that information, f prime is C equals 0. So just for a activity, we don't do a lot of activities in this class, but let's do an activity. I'm going to move the red dot really slow left to right like this multiple times. And if you see the location of where C is going to be, that critical number, just yell out stop. Right, let's give this a try. 1, 2, 3, go. Stop. You folks are really good at this. That's awesome. So that's our activity. It's really hard to do a math activity, but there's one. That's the right location. I would agree with that. I just need to change colors of pens. Let's go down to blue. I think we're about right there where folks said stop. A little bit of lag, so I'll just kind of move it to the left. It gives us a point right here. And what we can say for sure about that point is the slope, which is equal to m, is 0. But that's the same as the derivative of f at the number c, because the derivative gives us the slope of the tangent line at any value c that we plug in. So that's right here. Once again, f prime at c equals 0 is the conclusion by Rolle's theorem. They're essentially saying there's always going to be a horizontal tangent line, but then they're saying something even further. If there's a f prime at c equals 0, we also found a local maximum. It's local as the way I said it, but it's also absolute. It's the highest point on this graph. It may not have been, depending on how you drew your graph, but absolute maximums are also local maximums. And this is pointing us in the direction of that right here. So that's finally the full content of Rolle's theorem. Any questions or comments about it? Okay, so it's just a set of conditions. If 1, 2, and 3 holds, then those conditions tell you where a critical number will exist. Let's try this out immediately on a problem down below. I'll take a copy paste up here, since this is our Rolle's theorem. Let's try it down on example 1. So it says on example 1, and this is pretty much exactly how the problems are going to look in the homework. verify that the function satisfies the hypotheses of Rolle's theorem on the interval 0, 7. Let me highlight this portion. Sometimes this is the most confusing part of the problem. We have three hypotheses that we have to check. There are these three up here. Those are the hypotheses. And we have to check every single one of them. Honestly, it's not as bad as it sounds. Let me show you how I'd probably answer this kind of question. Let me click on this. I don't know why that keeps going away. Because we're talking about, well, first, continuity, I probably would just turn to the section that involves continuity. Let's go over to, it was a while ago, section 2.5 says information about continuity. If you go through here, you'll eventually stumble across some really amazing theorems. Theorem 7 is the big one. In fact, let's just throw it on our notes. Zoom in just so it copies and pastes as well. So first thing I'm going to do in the solution is cite this information. So this is from section 2.5. And that was a long time ago. We've been through a lot already in this class. But this theorem 7, ignore the red circle there. It says the following types of functions are continuous at every number in their domains. They are polynomials, rational functions, root functions, trigonometric functions. But what we have today is a polynomial. That would be a degree 7 polynomial. So we can say immediately, since f of x is a polynomial, it is continuous on 0, 7. 0, 7 is the domain that was given for this function, and it's continuous on any domain it would be given. It's continuous on the full real number line as an entire function. So that's condition number 1. Next, it has to be differentiable on the open interval from a to b. But polynomial functions, same issue. These are completely differentiable functions. So we can say here on part 2, also, f prime must exist on 0, 7. So if we take the derivative of this, it still is a polynomial. It's of degree 7. It would just be reduced down to degree 6. So that would still be a derivative that exists. But we say exists on the open interval from 0 to 7, since we haven't defined differentiability on the boundary points. Last thing we have to do is, well, really parts 1 and 2, you're just making a comment. So if all you put on your paper is, well, this function is an exponential function, it's continuous on differentiable on the entire real number line, that's completely fine. But for condition 3, that's something we actually have to calculate. I'll highlight this one in yellow, so here's our calculation. Really, it's not too bad. It's just a requirement that the function values match at the endpoints. So let's calculate f at one value, f at another value. Has anyone spotted what should go inside here for f of a, or here for f of b? Exactly, we just go right to that interval, throw in the values. 0 and 7 go here. And notice the function is kind of nice. It's in a factored form. This would turn into 0 cubed times 0 minus 7 power 4, but that's just 0. Put 7 inside the function, and they will turn into 7 cubed. 7 minus 7 to the power 4. That's also 0, thanks to the 7 minus 7 in there. So we can say f of 0 equals f of 7. And we just checked hypotheses 1 through 3. We can now say, therefore, f meets the hypotheses of Rolle's theorem. So we did it, folks. We meet the hypotheses. Now, here's one thing that's always a little bit weird about math. This is a powerful and technical theorem. It tells us that there's a number c between 0 and 7 for which the derivative of f at that c value should come out 0. That's great, but the theorem does not tell you how to find it. Depending on the actual function, it's going to be a new ad hoc solution for for each function. So really, we're working on equation solving. We've dealt with things with logarithms, exponentials. Here, we'll just deal with a polynomial. Still, the major trick we want is factoring is our big go-to. So now it says for our next part, find all numbers C that satisfy the conclusion of Rolle's theorem. Let's write down the conclusion here first, just to be careful. There exists C in 0, 7, or you could say instead 0 less C less 7. That's almost a little bit safer if you're used to inequality form of these kinds of intervals, such that the derivative of f at that number C is 0. In other words, we found a critical number is the whole content of Rolle's theorem after we satisfy these conclusions. But to actually find that number C, here's what we're going to do. Go back to the f of x and let's differentiate it. I'm going to recopy it here so we're not scrolling up and down a bunch. F of x equals x cubed times x minus 7 to the power 4. Now we just differentiate that function. It's not too bad. It is a product rule, and I wouldn't want to expand this thing to undo the product rule. Power 4 is just too irritating, too much algebra to get through. So instead, let's think of it like this. F prime of x will be equal to, first differentiate your x cubed, we get a 3x squared. Then multiply it by x minus 7 to power 4, completely copied. Then plus for the product rule. This time we're copying x cubed, so there it goes. And now we multiply by the derivative of this function. Now we have to be careful, sort of. This is a chain rule, right? The outer function is the power 4 function. The inner function is not x, it's x minus 7. So this is a bona fide chain rule problem. It's just one of those chain rules where we didn't see it, we actually don't get in trouble. That's kind of weird. But it's always good to see it just to make sure. If it was 7 minus x, that one would get us in trouble if we missed it. So this is the inner. And so when we go to do this derivative, first power 4 comes down. It's now power 3. Then copy x minus 7 inside that function that's cubed. Then multiply by the derivative of that inner function. But the derivative of x minus 7 is just a 1. So our careful work on chain rule didn't give us anything, but again, it's always good to spot them because if it was 7 minus x, we would have multiplied by -1 right here, and now it makes a huge difference all of a sudden. We got it, folks. That's our derivative. Now, even when we were in chapter 3, we didn't settle for this right here. We said we still want to simplify it. It's really for this work that we want to take all that time simplifying. First thing I'm going to do is just clean it up. 3x squared, x minus 7 power 4 plus 4x cubed, x minus 7 power 3. So I've just simplified things, the times ones, moved the 4 in front of x cubed. Next thing we want to do, if we're trying to find something set equal to 0, and we need solutions, we really should try to factor this thing. So common factors between 3 and 4, nothing of interest. But between x squared and x cubed, we would factor out the smallest power, x power 2. Likewise, between x minus 7 to power 4, x minus 7 to power 3, we factor out the smallest power between those two, x minus 7 to power 3. Then factoring is just a clever form of division in a certain sense. We are literally dividing x squared, x minus 7 cubed, into both of these terms. By the red dot, when we do that division, x squared is canceled, 3 remains, and x minus 4 to power 1 is the only survivor. So 3 times x minus 4. Then we do it again, throw in our plus, divide x squared here by the red dot, and we just get a 4x. And x minus 7 cubed divides this cleanly. It's now just gone. Yeah, go ahead, sorry. Oh, sorry, right here was an x minus, yeah, sorry for that. X minus 7 right in that location. Thanks for spotting that. That was invisible to me. You told me where it was, but I had to stare at it for a moment to find it. That should have been a 7 to 7 right there. So then it's a 4x, and we can close the bracket. Does that look right to folks so far? Okay, so we've done a pretty good amount of factoring just at this stage. Next thing we can do is just clean this up even more. Let's expand and combine like terms. This is now x squared, x minus 7 cubed, 3x minus 21, plus 4x. And last one, I'll put it over here. This finally has turned into x squared. Let me give that a little bit more space. X squared, x minus 7 cubed. We can demote the bracket. It's not as special anymore. I'll put a parenthesis on it. This is 7x minus 21. So we have the derivative, and it's in its most simplified form, especially for our purposes, because next we solve that equation. For the notes, we'll go to the next page. And here's what's going to happen next. We need to solve f prime of x equals to 0. At this stage, you could rewrite this as c if you like, or keep it at x. At this point, it's really just a stylistic choice. If you write your answers as x on the very last step, I'm okay with that as well. But what I'm going to do is my very last step, I'll write my answers as c equals whatever we find. But for the moment, let's just solve it as an ordinary problem. Only way that's equal to 0 is if the first factor is 0, or the second factor is 0, or the final factor, 7x minus 21 equals 0. So now we had a degree 6 polynomial equation set to 0. Let's just split into 3 separate equations. We can find the solutions immediately. X equals 0 on the first term, the first equation from the first factor. On this one, it has a solution of 7 with multiplicity 3, but we just throw in the 7 for that one. We're not worried about complex values or anything fancy. Here, add 21, divide by 7, and we'll get a value of 3. Now, this is the tricky step about Rolle's theorem. These are not all the correct solutions. One of them is correct, and there's 2 that are not. Anyone see what wouldn't work for the conclusion? 0. Absolutely, 0 is really gone from this. Anyone see another? 7 as well. And here's the reason why. This is something I personally find easy to forget, especially when we're on the bottom of the page here. Rolle's theorem said there's a number c in 0 to 7 for which the derivative is 0. But we put an open parentheses to say we're not talking about the boundary points at all. We're talking about the interior between 0 and 7. Or think of it this way. That means the only critical number was 3 because it's between 0 and 7. So let's make our conclusion look like this. The number, let me spell number correctly first. C in the conclusion is C equals 3. So that's what we're looking for with Rolle's theorem. Well, we did it, folks. Rolle's theorem gives you a critical number in a specific location. Well, it guarantees that there will be at least one. Then it becomes our job to find it. Really, all we're doing is saying the derivative equal to 0 and solving. Like we mentioned before, this turns into an extremely common technique in the entirety of these notes. We'll see it over and over again, with just a few exceptions. Any other questions, folks, on getting through this one? Yeah. The 3x squared, right? Oh, I forgot my 3. That 3 absolutely should have copied down. 3 would go here. It would have gone here. Thanks so much for spotting that. And it would have gone right here as well. Good news is we could have divided into the 0 and still wouldn't affect our solution. We still have 0 from that equation. Thanks so much for spotting that thing, though. All these things highlighted are things that I left off. I appreciate everyone's careful eyes on helping me through these notes. Try to go a little bit slower on the next ones and not drop things. But other questions so far, folks? Okay, well, if we have Rolle's theorem, that's a nice one to get a critical number like this. But Rolle's theorem is restrictive. If you still want to use a theorem like this, but you didn't want your points to match up. If, for example, you want to move this point a little bit higher, Rolle's theorem is out of the question. but you can actually readapt the theorem to that situation. Move one of the points higher or lower, and you have the mean value theorem instead of Rolle's theorem. So that's the bigger one in this section. The reason our author titles it the mean value theorem is between the extreme value theorem and the mean value theorem, that's all you really need, aside from a bunch of clever tricks, to prove the fundamental theorem of calculus, which is how we're going to reverse differentiation in a certain sense. So this is one of those little magic ingredients we'll need later on. And here's what Rolle's theorem, the mean value theorem looks like. It's highlighted in yellow since this theorem is quite an important theorem. In a calculus class, there's almost a guarantee that this would be on an exam, probably exam 3, a good chance on the final exam as well. And here's what it says. We want f to be a function satisfying just 2 hypotheses this time. As promised, the function never had to match on the boundary points, so condition 3 is taken away on this theorem from the Rolle's theorem, but we still require continuity, we still require differentiability. Continuity is on the closed interval from A to B, differentiability on the open interval. And it says, well, if you satisfy just the 2 conditions, you'll find another number C in AB such that the derivative of f at C is, well, now it's that. We need to discover, what does that mean? Why is this even called the mean value theorem? Does it appear to be averaging anything at all? So that's the setup so far. Now let's illustrate it and see just what's going on. First, any questions or comments, folks, about the theorem content so far? Okay. I think the biggest mystery in this theorem is the thing highlighted in green. So let's now do a really careful plot, see how this situation goes together. I want to make this a little bit bigger. Like before, just focusing on quadrant 1, here's our A, here's our B. I'll plot the function in, we have a lot of colors already. Let's go with black for the function, so it's not getting too busy. We can say we start right here if we'd like. Here's the point for f of A, 1 point on the graph. Now, if it was Rolle's theorem, f of B would have to be here. There's no other way to go. But now we can change it up. Let's put it a little bit higher, since if it's the mean value theorem, it is allowed. So this height on the y-axis is the location of f of B. Next, I'll draw the curve. I'm going to do kind of a weird kind of increasing and then leveling off kind of curve. Guess it does come down a little bit into this location. This is y equals f of x in black. So that's where we start. Now, next thing we're going to do is, well, this f of b minus f of a divided by b minus a. Anyone know what that really is in essence? It is a slope, exactly. It turns out that that is the average range of change of the function. Let's put this on the plot and discuss that next piece of the theorem. So I'm going to put a thin line going from here to here. Let's call this, well, it doesn't necessarily need a name, but what we want to calculate on this is its slope. So I'll put another arrow and write m is going to be, let's think of how you get the slope. You subtract the y values. So you'd be taking f of b minus f of a. Then you divide and you subtract by the x values in the same order. So b minus a down below. And that's exactly this thing right here. Now, if you take a value on one endpoint, a value on the other endpoint of a function like this thing has a name. This is the average rate of change of y equals f of x from x equals a to x equals b. It's not a secant line, so that's why this is kind of an interesting concept. We just have a simple average rate of change. Well, that average rate of change is the whole reason this is called the mean value theorem. In statistics, mean and average is sometimes thought of as a synonymous wording. And so we're talking about an average rate of change type of theorem when we say mean value theorem so far. Now, what the mean value theorem is saying is there will be a number C between A and B so that the derivative of f at C matches the average rate of change of the function altogether. This one's kind of hard to find though, but we can still practice. The way I would find this number C is with a little bit of extra tricks here. If we were doing it on paper, probably what I would do is take this green line here, draw it in, and just imagine moving that line up or down and see what happens to the curve. Using technology, it's slightly easier. We can copy that line. This is cheating a little bit. Paste it down. And what I'm going to be doing is just moving this line. I'm going to move it up. And what we'll do for this second activity, our second big activity for the class is just yell stop the instant it looks like a tangent line. All right, so I'm going to move it down slowly and holler stop when it looks like it's tangential. This is actually really hard to drag. Let me try again. So, about there. Yeah, right at that location, we have a tangent line. So this is the key spot right here. If we project down, we found a number C. And yeah, it is between A and B, so that this line right here becomes tangent. The line of this will have a slope m. That slope m is the derivative of f at C, which becomes the average rate of change, f of b minus f of a, divided by b minus a. So the mean value theorem says, as long as you have continuity and differentiability, both working at the same time for your function, there will be a number between one end and the other end so that the tangent line slope or the derivative will match the average rate of change of the function, that slope down below. So very interesting theorem. This theorem turns out to be extremely important when we unwind derivatives, looking for antiderivatives, dealing with the fundamental theorem of calculus. So it's kind of a strange theorem. Our whole goal in these notes is just to practice the theorem, become familiar with it, much like Rolle's theorem. Any questions at all, folks, before we start out? Okay, let's give this a try then on our first problem right here. Again, let's copy down the theorem just so it's available. I mean, we're just barely using it. Okay, so here's the mean value theorem once again. It says on this problem, verify that the function f of x equals e to the power negative 2x. This one's defined with domain 0 to 1, inclusive on the boundary points, satisfies the hypotheses of the mean value theorem. So that's our first thing to do. And in the homework, let's take a look at the Moodle website for just a moment. I'm just going to copy and paste in some information and come right back. I want to point towards this part of the homework right here. Okay, I think we're in business now. So we have a function, we're satisfying the hypotheses of the mean value theorem, but this is definitely part of the exercises in this homework assignment. It's not too bad, but it just feels weird at first. And I'll show you what it would do on this one as well. What's weird is we're not really calculating anything. We're just writing down what we know about this function. An exponential function has domain all real numbers. If you differentiate that function, it becomes continuous. And the ordinary function itself is continuous and differentiable. So pretty much all I would say here about the hypotheses is this. Let me point the arrow down and say, since f of x equals e to the power negative 2x is an exponential function, it is differentiable on negative infinity to infinity, which is equal to R. So taking that function without a domain condition, that's the foregone conclusion. It's as nice as possible, just like polynomials. So what I would say next is, therefore, f is continuous on a restricted set from 0 to 1 if it's continuous on all of R. But how do I know that? Well, you can see that big theorem 7 that says all these different functions are continuous from section 2.5. Or we can use another theorem that says differentiability implies continuity. Already knowing that's differentiable tells us it has to be continuous on this set. And now we can say if it's differentiable on the entire real number line, it's also differentiable on the restricted set from 0 to 1. So pretty much that's all is expected for this portion of the exercises on these. Really, the reason the author puts that into the homework assignment, verify the hypotheses, is he just wants to know that you took a look at them and you thought about them. Because these theorems are dangerous. If we don't actually meet the hypotheses, anything can happen. There might not be such a number C whatsoever. So that takes care of this first portion. The second portion is when you're really calculating stuff. Now we're going to find that number C that's going to give us, oh, I didn't actually copy the rest of the theorem. That's going to give us this result. F prime at C is going to be equal to f of B minus f of A divided by B minus A. So that's what we're trying to solve for at the moment. Now, the mean value theorem is tricky because sure, there's less hypotheses to check, but the equation solving is a little bit more involved. This is a good one to split up into like a 3-step approach. My first step would be just calculate the derivative at x. So f prime at x right away. It's an exponential function, e to the power negative 2x. This one's also a chain rule, and it's one of those chain rules that really does actually matter. Here, the outer function is the base e exponential, and the inner function is the power 2 to the x. Anyone happen to have the derivative of this function? Exactly, negative 2e to the power negative 2x. But you've got it down absolutely, yeah. So differentiating the first one, that's what gives you e negative 2x. Differentiating that negative 2x gives you the negative 2. Good call. So now, we're not on step 3. Let me try again. Step 2. Must be late in the week. Counting's getting harder. Step 2, we're just focusing on that slope right there, the average rate of change of the function f of x on 0, 1. That's pretty much all we're calculating. So let's go over here and calculate f of b minus f of a divided by b minus a. When we go to do this computation, we find our a and b, just like with Rolle's theorem, from that closed set right here. So this will turn into f of 1 minus f of 0. Our b is 1 and our a is 0, divided by 1 minus 0. And really, that's not too bad. We just need to go to the function f right over here and do 2 evaluations and simplify. First, f of 1 is e to the power of negative 2 times 1. F of 0 is going to be e to the power of negative 2 times 0. And the denominator is a glorified 1. Honestly, probably don't even need to copy it on this step. Denominator is 1, and division by 1 just gives us that. So let me leave it to this stage so we can still see that conclusion. So if we simplify this a little bit further, this is just e to the power of negative 2. Right over here, this is e to the power of 0, and e to the power of 0 is just a 1 altogether. So minus 1. So e power negative 2 minus 1 is the average rate of change of the function on the set 0, 1 right here. Now in step 3, we take both results and equate them together. I'm still going to leave it as an x and only go to the number c when I'm writing down my final conclusion. But keep in mind, c is between a and b. Let's write it here just as a reminder. Over here in the conclusion, c has to be between 0 and 1. In inequality form, it would look like that. As interval notation, we just say C is in parenthesis 0, 1, close the parenthesis. So let's equate both of those and see what we get. It's going to be -2 e to the power of -2x is now set equal to e to the power of -2 minus 1. So this is the equation that we have to solve. Not like what we did before, where we were dealing with the polynomial. We pretty much just factored it, set factors to 0, and we were on our way. This one's a little bit worse, but there's a good news with this one. If you see things like a logarithm or an exponential, try to get it into one spot. It's almost isolated. We just need to solve for e to the -2x to start. So let's just divide by -2. When we divide by -2 on this thing, we get e power -2x equals e power -2 minus 1 divided by -2. You can change the format of this if you want 1 minus e squared divided by +2, but I would usually just leave it in that format. That's more of a stylistic choice at that stage. Anyone see what the next step ought to be to this stage? Exactly. Take the natural log of both sides and you kill the exponential right here. So it'll look like this. Natural logarithm of e -2x equals the natural logarithm of e power -2 minus 1 divided by -2. Oh, dang, that looks pretty ugly. Let me try to write it in a better way. I'm just going to leave it as a stacked fraction like we saw there, instead of writing it as a line. Natural log e -2 minus 1 divided by -2. You could do all sorts of fancy things to make this simpler, properties of logarithms and so on. But honestly, we're not doing too much with this number other than validating if it's between 0 and 1. I'd probably just leave it right in that format. But here's the big reason why we took the natural log. Base e exponential is gone, and now we move the arrow upwards. -2x equals natural log e power -2 minus 1 division by -2. That is an overexcited negative sign. Let's fix that. That just looks weird. Looks like a mistake. Then divide by -2 and x equals -1/2 natural log e power. Let me fix that parenthesis here. E power -2 minus 1 division by -2. So my claim is that's the answer to this problem. You could leave it as x, call it a c if you'd like. I'll probably call it in C on the next step. That I would definitely do, even though it's optional. The thing I would definitely do with this is, I have no idea what that number is. It's almost impossible to see unless you are extremely good at analyzing these kinds of numbers. I just need to check if it's really between 0 and 1. It cannot equal 0, it cannot equal 1, and it cannot be on the outside of that interval. So now we need a decent calculator.
So the square bracket imply that and like example 0 would be inclusive, right?
Exactly, yeah. So if we did have brackets right here on that conclusion, we could have said less than or equals here. 0 and 1 would have been possibilities, absolutely. Other questions so far? Okay, let me try and grab that quick calculator. I forgot where my stuff is. Let me kind of move that around. Oh no, it disappeared. There we go. So we're just putting that in. -1/2 natural log e power -2 minus 1 -2. I can't quite see that number. That's kind of suspenseful. But hey, looks like we're in good shape, folks. This number is between 0 and 1. It's 0.4193 if we were to round on this. I'll just round it to a meager 0.42. I like the exact answer here, but sometimes it's a pretty good idea to approximate. This is one of those times, 0.42, because now we can check, yes, it is between 0 and 1. It's in this set, or excuse me, in this set by blue, in blue right here. That tells us we really have the right answer. I'll box both of these, since the answer is really in both positions now. One of them approximated, one of them exact. So that's the process with the mean value theorem. Any questions, folks, on getting through this one? Okay, so what it's saying altogether is the average rate of change of this function is e power -2 minus 1. And if we go exactly to 0.42 on the graph of this function, then the rate of change at that instant matches the overall rate of change of the whole function from 0 to 1. In other words, we can put this on a graph to take a look. Let's see if we can make that expression really work out. So let's close this. Let's put in f of x equals e power -2x. There's our curve. We probably should zoom in on this a lot. We only care of between 0 and 1. So let's put in 0 less x less 1. That was the whole curve we were concerned about, that quantity right there. Let's blow this up a little bit and see if our work really actually matches up. Okay, back down to the graph. We'll go on to the second page. This is pretty much our check at this stage. What I would do with the graph is, next, put down a line that goes from here to here. Let's try to draw that straight line. That's my best attempt. I'll leave it like that just to convey, doesn't have to be perfect. Next, grab this line. Oh, I want to leave it just where it was actually. Let's duplicate it and take this one right about here-ish. Looks like it's tangential. Would you all agree? Awesome. So the point of tangency would have been right here. And if I had to visually estimate it, I'd say maybe 0.45 or something like that. We've got a 0.42. We're actually super close just doing it purely geometrically like this versus following the method and getting the more exact value. But this is a good thing to take a look at. It's kind of nice for both the Rolle's theorem and the mean value theorem. You have immediate check just by looking at the geometry of the problem. So let's call this a check. And I guess we can check the check to say it worked out. We really do have the plausible correct value right here. Well, any other questions or comments, folks, on getting through this one? Okay, so that's the idea of the mean value theorem. And like before, we have to be really very careful about these hypotheses, both for Rolle's theorem and the mean value theorem. That's what the next example is going to be about. If these hypotheses fail, then when you go to try to do this work, solve for the number c, really wild and unexpected things can happen. So that'll be our next problem. Let's take a look at this one here. So f of x is not a polynomial. We have a rational function this time. It's x minus 3 to the power of -2. Or you could write it as 1 over x minus 3 power positive 2 if you like. It says, show that there is no value of c in 1,4 such that the derivative of f at c equals f of 4 minus f of 1 divided by 4 minus 1. So that's the whole problem. We want to show this is impossible. Then we have to explain why this didn't contradict the mean value theorem. This is the conclusion of mean value theorem that you could actually solve this. And they're telling us it's impossible. We have to explain why. But really the way to give that explanation is just go through the whole method again. Here's step 1 for the conclusion of the mean value theorem. You take the given function and just differentiate it. So let's differentiate that thing. So here, f prime of x. Once again, it's a chain rule, so let's be careful with this one. -2 is going to come down as a coefficient. The new exponent is 1 less, so now it's at -3. And then we multiply by the derivative of that input there. So x minus 3 goes inside here and here. But once again, it was a kind of a silly problem where this derivative is 1. So the chain rule, although important, didn't really matter on this one. Still, it's good to see where they happen. This turns into -2 x minus 3 to power -3 times 1. And so we can say f prime of x equals, I'll leave a -2 in the numerator. Let's convert that exponent to positive. It might be convenient when we do the equation solving. So x minus 3 to power positive 3. So step 1 is done. We have our function. Next thing we do is we're going to calculate average rate of change of y equals f of x from x equals 1 to x equals 4. That means that this function, it truly had domain 1 to 4 that we're considering on this problem. We have to calculate those actual values to make this work out. But the conclusion is about the open set, 1 to 4 like this. We're trying to show that there's no C between 1 and 4 written this way. But now the average rate of change, it's really just this right here. Calculate f of 4 minus f of 1. 4 minus 1 becomes, let's see, we're placing this 4 right inside here. We're putting it into the original function f of x. To me, that's another one of the confusions of this problem. There's a lot of functions on the table. There's the original, there's the derivative, but this is talking about the original function. So we go back up to the top here. It might not be a bad idea to code it in green just to be careful with it. So this will be 4 minus 3 to the power of negative 2. That's just 1 to a power, so it's a glorified 1 altogether. Minus f of 1, that's going to be 1 minus 3 to power negative 2. That's something we actually have to calculate. Divide by 3. So that's where the problem sits so far. Then in this location, we get a 1 minus. This one is turning into negative 2 power negative 2. Division by 3. Honestly, this is turning into a review of exponents and exponent laws. Let's focus on that power negative 2 and see if we can simplify this a little bit more. This is 1 minus 1 over negative 2 to the power positive 2. I just threw it into the denominator. As we can do a little bit more exponential surgery on that, that's now just 4 altogether. Even though it was negative 2 to a power, that power is even. That's going to turn into a positive quantity right there. It's 1 minus a 4th. Divide by 3. So now it's a complex fraction. It feels like it just keeps getting worse the more we do to it. But it's settling down because we can clear the denominator 4 like this. Multiply by 4 over 4. 4 distributes inside, giving us a 4 right here on the red dot. Minus 1. It clears the denominator in this location. Divide by 12. So now we have 3/12. The arithmetic is worse than the calculus on this one, but we're almost there. It settles to 1/4 altogether. So that was our step 2. Really, you get a 0.25. If you put this in the calculator and got an exact 0.25, that's okay in your solution as well. But sometimes this is good practice because you never know when you just have to deal with exponents and you can't just put things in a calculator. So on to step 3. We equate our two values. We're really just going to this portion here. I'll write it as f prime of x is now equated with, let me put in this just to connect the steps, f of 4 minus f of 1, 4 minus 1. So we grab our prior information. The derivative of f at x is that quantity, negative 2, x minus 3 to the power 3. On the right-hand side, after some tedious work on this, we got to exactly 1/4. And so now that's our equation to solve. Like we mentioned, all of our equation solving is like a new ad hoc situation every single time, and the theorems don't tell us how to deal with these. But this one's not too bad. The good old cross product really does the deal for us, only because it's two fractions separated with equality. If I had an extra fraction on the right-hand side, this wouldn't work. But you could just send x minus 3 cubed to the right into the numerator, 4 to the left into the numerator, and that's a bona fide cross product. Kind of nice to do one of these since usually we don't do cross products at all, but occasionally it will come up. So we get negative 2 times 4 on the left, 1 times x minus 3 cubed on the right. So now it's negative 8 equals x minus 3 cubed. Solving this equation is just exactly the same as if you were solving this equation. You need an inverse function to get rid of the base c exponential. We had to choose the natural log. Down here, we need a function inverse to the cubing function. Anyone recall what it should be? Exactly, we hit it with the cube root function. That's just like the step of taking the natural log of both sides, but it's a new function, so it's a new inverse. Cube root goes here, and it will go there. Purple because those are always interesting steps when you take an inverse function. On the right-hand side, the power 3 is completely killed off by the cube root, and you just are left with an x minus 3. Left-hand side, cube root of negative 8 is a negative 2. So we're just about there. Add 3 to both sides, and we get positive 1 equals x. It could be, yeah, if we're dealing with complex numbers, but we're only going to do the real numbers for this one. Yeah, really, there's 3 different cube roots. They're all on a unit circle, separated by the same distance. It's wild. If it was the 4th root, we'd get 4 solutions and so on. But here, we're only picking off the purely real root. Other questions so far? Yeah. Oh, gotcha. That step was where in the world of exponent laws, if you have something that goes like, say, a to the power of negative n, you can always flip the position of that and go 1 over a to the power positive n. And there's also a second version. If you have, say, 1 over a to the negative n, and you need that negative n to come out positive, just flip its position once more, and it becomes positive in the numerator. So kind of the way to think about it is, if you decide to move this from the numerator down to the denominator, go for it. All you have to do is change the sign, and vice versa. Other questions about that so far? Okay, well, let's see what's happened to this problem so far. We have a solution, x is 1, but we need to be careful, right? That solution had to be larger than 1 and less than 4. So now that solution is thrown away. We're on to this portion. Why don't we have a contradiction? But first, let's say that statement. Since 1 is not inside 0 to 1, it does not satisfy the conclusion of the mean value theorem. That deserves an exclamation point because that means, well, it appears something went wrong, right? The theorem had a guarantee, it had a promise, and that was broken. But was it broken really? We always have to consider the hypotheses about the mean value theorem, and that's kind of what this problem was really about. We went and cranked out the conclusion without even thinking of the hypotheses. So let's backtrack this a little bit. Let's grab this function once more and think about those hypotheses. So we're on the phase of the problem where we're answering why it does not, in fact, cause a contradiction. No promise was broken. We were never actually expected to find a value inside 0, 1 that gave this kind of equation right here. But we have to say why at this stage. Anyone see what it could be? Exactly, we have lost continuity on this one. F of x was defined in this way. Let me just rewrite it here. F of x equals x minus 3 to the power negative 2. You know, it's more obvious there's a problem if we call it 1 over x minus 3 to the power positive 2. Now it really highlights there's a problem here, right? And it has domain bracket 1 to 4. Now, if that domain went, say, like 5 to 7, we would have gotten a different number here, but we would have found the right number in the conclusion because it would have been continuous on that domain. Just like you said here, x equals 3 is an infinite discontinuity. And so this function did not satisfy the hypotheses of the mean value theorem. Lots of writing on this problem. Think I can fit that in there? Mean value theorem. So the theorem wasn't broken, it just had a discontinuity, but the theorem insists right away, you're both differentiable and continuous. Continuous on the closed domain, differentiable on 1 to 4 as an open domain, an open set. Well, any questions, folks, with the conclusion of this kind of a rather long problem? Okay, well, we don't have a great deal of time, but I did still want to show you this last application because to a certain degree, this is the punchline of the mean value theorem. And the mean value theorem is an extension to Rolle's theorem. So this is where it's really all going. All of your exercises, homework problems, they're really just practicing the theorem so we know what it's saying, how to work with it. But this is what it provides us. It provides us with a powerful theorem. This theorem says if the derivative is 0 for all x in an interval, then f must have been a constant function. This is already a way to undo a derivative because we've said in the past, if f of x is a constant function, like say 5, that's a constant function, then its derivative at x, sorry, confusing thoughts there, must be 0 because it's a constant. This now goes backwards. It says if you started with a 0 derivative, you can unwind this and say your original function must have been some constant. This is the first hint on how we're going to begin undoing derivatives. We'll call them antiderivatives. Going here to here is finding one antiderivative. Let me write that over here where it would be more apparent. Going from f prime of x equals 0 to f of x equals c, where c is a constant, is finding an antiderivative. This will be the last section in chapter 4. Section 4.9 is all about antiderivatives. It'll be a great chance to re-practice differentiation because the check on any antiderivative is differentiate your answer and see if you got the right thing. So the last thing I placed down here is not as huge of a punchline to me, but still kind of a cool little tool here. It says if your functions match in their derivative, they have the same rate of change at every single point, same slope. For all x in an interval, then if you subtract them, that thing is constant. In other words, if your derivatives are the same, your functions are the same, they only differ, once again, by a constant. There's something kind of interesting going on with these constants that we'll have a lot of time to discuss once we get further and further on into our antiderivatives territory. Using that information, you could prove like the most nastiest trigonometric identity ever, that arcsine of that is arctangent of that. There's no way I could prove this if I was only using ideas from trigonometry. I would probably just quietly sob and give up. But if you use these ideas, you can make that happen. Just differentiate the left-hand side, that's the hard part. Differentiate the right-hand side and you'll find they're actually equal. That means you can write down this equation, then you would solve for that constant, and it turns out that's the constant, pi over 2 right there. So that's where all of this is going, but unfortunately this would take another 20 minutes-ish to solve this one here. If you're curious about this problem, let me know though, either after class or by email. I'm very happy to solve this one and post it onto the notes. But I think this is a good stopping point for us. This is not a 3-minute problem. Any last questions, folks, before we call it a night? Okay, well, have a great night, everyone. When we come back, we'll do more of this kind of work. We'll be in section 4.3.